Hello, and welcome to episode 5 of my 6-part series on an intro to AMC 10. My name is Michael Liu, and I'm from Agora Math Circle. In this video, we'll be going over complex numbers. So first, I'll be going over the basics of imaginary numbers, and then I'll cover the basics of complex numbers. Then I'll go over conjugate pairs, the modulus of a complex number, and Eulers Formula. After that, I'll go over the graph of a complex number, power operations on complex numbers, and finally, I'll end it with an example AMC problem. So imaginary numbers are mainly represented by I, and I is equal to the square root of -1. So the reason why we say that that's imaginary is because if you think about it, if you multiply a negative by a negative, it should be a positive. So then, how is it possible that you could square a number and then get -1? So then that's why we have I. So I squared is equal to -1 because that's how it's defined. I cubed is equal to -I because I cubed is equal to I times I squared, which is equal to I times -1. I to the fourth is equal to 1 because it's just I squared again, so that's just 1. And I to the fifth is equal to I because it's I to the fourth, which equals 1 times I again. So you can always add or subtract 4 from the exponent of I and still get the same number. So we see that demonstrated with I to the fifth. We can subtract 4 from the exponents, and then we just get I, and I to the fifth is equal to I. Performing operations on I is like performing operations on variables. So we see down here, just treat I as a variable. 3i plus 2i is equal to 5i. 2i times 5i is equal to 10i squared. Well, here we can simplify 10i squared, which is equal to -10. And then down there, we have 5i cubed divided by I to the fourth is equal to 5 divided by I, which is equal to 5i divided by I squared, which is equal to -5i. So, two things to keep in mind here is that for an expression to be truly simplified, I cannot be in the denominator. So you can see here that we removed I from the denominator by multiplying both sides, top and the bottom, by I to remove from the denominator. And then this is equal to -1. So 5 divided by -1 is just -5i, or 5i divided by -1 is -5i. And also, in order for it to be simplified, you cannot have I to an exponent. So you see here we have I squared. Well, that's not simplified. So we have to replace I squared with -1, and 10 times -1 is equal to -10. Complex numbers are numbers that have both a real part and an imaginary part. So they would be things like 2 plus 2i, or -3 minus I. They can be graphed where the x-coordinate is the real part and the y-coordinate is the imaginary part. And I'll show an example of that later. I should still be treated similarly to a variable while performing operations on complex numbers. So we see here, we have two complex numbers, 5 plus 4i plus 2 minus 2i. That'd be equal to 7 plus 2i. And then down there we have multiplication of two complex numbers. 4 minus 3i times 2 plus I is equal to 8 plus 4i minus 6i minus 3i squared, which is equal to 8 minus 2i plus 3, which is equal to 11 minus 2i. So once again with complex numbers, you want to make sure that there's no exponent of I. So you see here that we got rid of the I squared by turning it into -1. -3 times -1 is equal to +3. And then also, you do not want I in the denominator. So in this case, conjugates would be useful, which I'll be covering shortly. So now I'll be covering conjugate pairs. A conjugate pair involves two complex numbers, where the real parts are equal, but the imaginary parts are additive inverses. So in general, they would be a plus bi and a minus bi. So that's a conjugate pair. They're often used to remove imaginary numbers from the denominators of fractions. So the reason why this works is because of the difference of two squares formula, right? Yeah. So basically, if you have a squared minus b squared, that's equal to a plus b times a minus b, in case you do not know that. So that's called difference of two squares. So we know that if we want to remove I, we can just find some way to make it I squared, and then we can simplify it to -1 instead of having an I. So that's what we can do here with the difference of two squares. If we multiply by the conjugate, so if instead we have a plus bi times a minus bi, well, using that formula, we know that's equal to a squared minus bi squared. Will that be equal to a squared minus b squared I squared? Well, you know I squared is equal to -1, so then that subtraction sign becomes an addition sign, so that'd be a squared plus b squared. So you can see there that we have an example problem. 3i divided by 2 plus 3i. Sorry, 3 plus I divided by 2 plus 3i. So we multiply both sides of the fraction by the conjugate of the denominator to remove the imaginary part. So remember, you want to use the conjugate of the denominator, not the numerator, because you want to make sure to remove the imaginary part from the denominator. It's fine if you have an imaginary number on the numerator, but you want to make sure that it's not there on the denominator. So we can see here, we multiply both sides of the equation by the conjugates, and then we expand this. 6 minus 9i plus 2i minus 3i squared, and then we can use our difference of two squares formula here. 4, which is 2 squared, minus 9i squared, which is 3i squared. And then on top we simplify that to 9 minus 7i, and on the bottom we simplify it to 13. So this 9 minus 7i divided by 13 would be the simplified form of 3 plus I divided by 2 plus 3i. So now let me go over the modulus of a complex number. What it is that it is the square root of the sum of the squares of the real parts and the imaginary parts. So in general, for a complex number x plus iy, the modulus would be the square root of x squared plus y squared. So that's what that top part means. The imaginary part of the number is iy, and the real part is x. And then when you take the square root of the imaginary part of the number, you don't include the I. You only include y, not I. So only the coefficients. Also, notice that if we were to graph the complex number, the modulus would represent the distance from the origin to the graphed point. And I'll be showing a graph of that later, and I'll talk a little bit more about that. So if, for example, we had a complex number 3 plus 4i, to take the modulus, we just do the square root of 3 squared plus 4 squared. Remember, we don't include I when taking the modulus. That'd be equal to the square root of 25, which is equal to 5. So now I'll be going over Eulers Formula. It is e to the ix is equal to cosine x plus I sine x, where x is in radians. X must be in radians. If you put x in degrees, this formula will not work. So pi radians is equal to 180 degrees. Radians are just another way of measuring the degree of an angle, or the measure of an angle. So for example, suppose we have a complex number radical 3 plus I. Whenever you use Euler's formula and you want to find the trigonometric values to convert it to this form over here, cosine x plus I sine x, you want to factor out the modulus of the expression. So in this case, the modulus is 2, because remember, this is it just be square root of radical 3 squared, which is 3, plus 1 squared, which is 1. That's just 2. So in this case, we factor out the modulus, which is 2. And then really, it'd probably be best to write it like this, just to remind yourself that the 2 is still there. So you can see that the complex number would be in the first quadrant if it was graphed, because both of the numbers are positive. So we know that x must be between 0 and pi over 2, which is equal to 90 degrees. So in case you didn't know, if we have this coordinate plane, this is the first quadrant, second quadrant, third quadrant, and fourth quadrant. So first quadrant is positive, positive. So first positive will be the real part, second positive will be the imaginary part. Second quadrant is negative, positive, negative, negative, and then positive, negative. So remember that the first positive represents the real part, second quadrant represents the imaginary parts. Assuming you graph the real part on the x-axis and the imaginary part on the y-axis. So then you also have degrees. So let's say the imaginary number here could be graphed as this point right here. Well, in this case, this would be the degree. So if it's in the first quadrant, as you can see here, it's between 0 and pi over 2, or 90 degrees, because this line right here represents 0 degrees, this represents 90, or pi over 2, this represents 180, or pi over, or just pi, and this represents 270, or 3 pi over 2. And then this line also represents 360 degrees, which is the same as 0 degrees. So in this case, you can figure out that x equals pi over 6, because, well, you should have memorized these values, that cosine 30 degrees, or pi over 6, is equal to radical 3 over 2, and sine pi over 6 is equal to 1/2. So now we can convert into Eulers using Eulers formula. So you get e to the I pi divided by 6. But remember that we also have our modulus here. So the full thing would be 2 times e to the I pi over 6. If you do not understand this part, I would highly recommend for you to check out another online guide, because this comes in useful for many problems involving complex numbers. So now I'll be going over the graph of a complex number. So you can see here that we have complex number 2 plus 2i and its conjugate 2 minus 2i. Well, remember that we have the real numbers represented here and the imaginary represented here. So first we put the real number, we look at that. We have the real number, we find the real number, we see it's 2, we find 2, we look at the imaginary number, we see it's 2, and then we find 2 and we graph the point here. So if instead we have, let's say, -4 plus 2i, well, we first look at the real number, see it's -4, we look here, plus 2i, it'd be right there. So you see that this is the modulus, 2 radical 2. We can quickly verify that by saying, okay, so that's 2 squared is 4, and then 2i, well, 2 squared is also 4. That'd be equal to radical 8, and equals 2 radical 2. And then remember, we ignore the I when taking the modulus, and also when graphing. Because you see here, we just label it 2. So that's the modulus. But notice that if we draw this line down here and this line across, this forms a right triangle. So the modulus is the distance from the origin to the point. And you can just see that this is just a right triangle where the real part is this length, the imaginary part is this length, and the modulus is the distance from 0, 0, which is the origin, to the point if you graphed it. And now we can see here that we have the conjugate. The conjugate is just the reflection of the complex number across the real axis. And then we can see here that the degree would be equal to the negative of the degree here. So you can see here the degree is pi over 4, but here the degree is negative pi over 4. And in this case, when you graph it, you can't have negative degrees. If you go count, so remember, when you look at the degree of something, you always start from this part of the graph. That part right there. So we can look up, we can see that if it goes counterclockwise, then the degree is positive. If it goes clockwise, then the degree is negative. So we can also actually say that if we go all the way around, we can also say that this is negative 3 pi over 4. So pi over 4 is equal to negative 3 pi over 4. And that makes sense because we know previously that we can add 2 pi or 360 degrees to any degree we want. And it'll still be the same because 360 degrees is also equal to 0 degrees. And then over here we can just see that if we convert it to Eulers form, then we get, well, we get the modulus 2 radical 2. We see here that what's left, that it's cosine pi over 4. So the x, the degree in Eulers form, is the same as the degree if you were to graph it right here. And then you can also see that the degree here is the same as we graphed it right here. The negative pi over 4. So this is Eulers form, or this is a trigonometric form, and then this is Eulers form. And we notice here that the conjugates, the only difference between the complex numbers and its conjugates is that the exponent in Eulers form is negative. So this is just a graph to demonstrate a few concepts and just to see how they actually interact with each other. So now I'll be going over power operations on complex numbers. Euler's formula is very useful for taking large powers of complex numbers, as it would be very tedious to expand such expressions. So for example, let's say we have to find radical 3 plus I to the 24th power. The power is far too large to expand by hand, so we'll convert it using Euler's formula. So I mean, this just makes it much easier to find the power because it'd be almost impossible or take a very long time if you were to like write it out and say radical 3 plus I and then just write that out 24 times and then multiply it all by hand. That'd take way too long. So we'll just convert it using Euler's formula. While using our previous work, we know that radical 3 plus I is equal to 2 times e to the I pi divided by 6. So we see that here. We just substitute 2 to the e pi, 2 times e to the I pi over 6 in for radical 3 plus I. So we get 2 times, so radical 3 plus I to the 24th power is equal to 2 times e to the I pi divided by 6 to the 24th power. Well, then we can distribute the exponent to 2 and to the e to the I pi to the 6. So we get 2 to the 24th times e to the 4 I pi. So remember that we have the identity that if we have this to 24th, you just multiply the exponents. So if we multiply the exponents, we just get e to the 4 pi I, or 4 I pi. And then you don't necessarily have to expand the 2 to the 24th, unless the question requires you to. So sine and cos are periodic functions, meaning that they repeat, since they have a period of 2 pi. And if you think about it, it makes sense, because 2 pi is equal to, is the same thing as 0, and if you can add 2 pi to any other measure of an angle, and it'll be the same angle, or it'll essentially be the same angle. So since e to the ix is based on sine and cosine, we can add and subtract 2 times n pi from x for any integer n without affecting its value. Because remember, you can add and subtract 2 pi however many times you want. N just represents the number of times you do so. So we further evaluate this. 2 to the 24th times e to the 4i pi. That's equal to 2 to the 24th times e to the 0i. Well, now this space we can just subtract 2 pi times 2 from x. Because once again, remember that 2 pi, you can add and subtract it however many times you want from the measure of an angle. And that's what the 4 pi represents, the measure of an angle. And then we get e to the 0i. Well, anything to the 0i is just equal to 0. And anything to the 0 power is equal to 1. So that's equal to 2 to the 24th. And then if you forgot from last time, remember that e is just the natural number. Its value is equal to about 2.7. The exact value of e does not matter for our purposes, but in case you were curious, e is found by finding the limit of x as x approaches 0 of this expression right here. If you do not know what that expression, not as x approaches 0, as x approaches infinity of that expression over there. There should be actually I should be 1 plus that expression. If you do not know what limits are, don't worry about that because the value of e doesn't matter. I should probably write that out a bit better. The value of e does not matter for our purposes. Just know that e is useful for multiple things, and right now our main use for it is Eulers Formula. So now I'll be going over the example problem for this video. So once again for this topic, the AMC 10 actually does not cover complex numbers that often. So I'll be using an example problem from the AMC 12. So this problem is from the 2020 AMC 12A, and it's problem 22. It reads, let a sub n and b of n be the sequences of real numbers such that 2 plus I to the n is equal to a sub n plus b of n I for all integers n greater than or equal to 0, where I is equal to the square root of -1. What is that expression over there? Well, first of all, you have to know what sigma is. So this is called sigma notation. What it is that it's the sum of this. So you start out with n equals 0, you evaluate this expression as n equals 0, then you go up 1 to n equals 1, and then you evaluate this expression again. And then you go all the way up to infinity. It doesn't have to be all the way up to infinity, but it was marked here. So this number is known as the upper limit, so I can have it be anything. Like say I can have it be 7. And then the lower number is the lower limit. It doesn't have to be 0, it can be any number. So let's say I have it be 6. And then let's say my expression is n plus 1 divided by n. Well, you start with 6. You evaluate this expression, 6 plus 1 divided by 6, and then you move up 1. So then next to 7. And then you add what's next to that. So 7 plus 1 divided by 7. And then by that point, we've reached our upper limits, so we don't need to keep on going. Well, in this case, the upper limit is infinity, so you do keep on going. If you still don't understand what sigma notation is, you definitely want to look online for another explanation, because it's very certainly necessary to understanding this problem. Also, something else you might not know is what a sub n and b of n mean. They're basically their own functions. Well, they're sequences, which are kind of like functions, but they only have inputs for integers. Well, for natural numbers or whole numbers in this case. So they only have inputs from 0 to infinity. For the integers from 0 to infinity. So just think of them like functions for this matter. And sigma notation, it only counts in integers. So from 0 to infinity, it goes from 0 and then goes up to 1 and it goes to 2 and it goes all the way up to infinity. It doesn't go from 0 to 0 0.1 or 0 0.001. It only counts in integers. So just remember those two things for solving this problem. And it's still a very difficult problem that would be very, very difficult, almost impossible to solve if you have not had any prior experience with complex numbers. If you still want to give it a try, you can pause the video right now. Otherwise, I'll be going over the solution right now. So first, we'll look at the given equation. 2 plus I to the nth power is equal to a sub n plus b of n I. So if we square both sides, we get 2 plus I to the 2n is equal to a sub n plus b of n I squared. So then we can distribute the squared inside. Remember that property works in reverse. The same way we can also say that that is equal to 2 plus I squared to the nth power. Well, then we can also expand this. So that's a sub n squared minus b of n squared plus 2a sub n b of n I. Just you can just expand it. If you want to use FOIL, you can, or if you remember the formula for expansion of a binomial squared, you can also use that. It doesn't really matter. Well, the reason why we squared this is because you see over here on the sigma parts, you have a sub n b of n. Well, you see right here, we have a sub n b of n. So now we can replace the sequences here with whatever we evaluate this to be. So, well, we want to replace this with just numbers, not more sequences. So we need to find a way to only compare this part, but ignore this part. Well, notice that we have an I here. So what we can do is we can compare only the imaginary parts. So the way we write that is we just write I am and then put whatever you want in parentheses, which is only the imaginary parts. So he writes 2 a sub n b of n, it's equal to I am 3 plus 4 I to the n. And we should not have an I here because when you put I am, it doesn't include I. It only includes the coefficients of I. So if we had 3, if we say have 3i, we have 4 plus 3i, and we took I am of that, that'd be equal to 3. So then a sub n b of n is equal to 1/2 I am, and then that right there. So then we can plug it into the sigma. So we see here, this is our sigma. We plug in a sub n b of n to this, which is 1/2. We just plug this thing in, divide by 7 to the n. Well, then, because it's a sigma, there's a property where you can just move factors outside. I mean, if you think about it, if we have 1/2 a plus 1/2 b plus 1/2 c, that's the same as saying 1/2 a plus b plus c, right? So that's basically what's happening when we move the 1/2 from inside the sigma to outside the sigma. And we can also do the same thing with the imaginary notation thing. So now we get this right here. Well, we can, using the reverse distributive property, or the inverse reverse distributive property, we move the n's outside here. And then this becomes a geometric sequence. If you don't know what that is, don't worry about it. I'll talk about it in the next video. But it's an infinite geometric series, which means we can use the formula for the sum of an infinite geometric series. So we move over the 1/2 to the IM. So using the formula, we get 1 divided by 1 minus 3 plus 4i divided by 7. So once again, I'll go over the formula in the next video. So if you don't know what the formula is, you don't need to worry about it. In case you're curious about it, it's a sub 1, where a sub 1 is the first term. So in this case, 1 would be the first term, since the first term is n is this to the 0 power, since n starts at 0. A sub 1 divided by 1 minus r. And then r is just what's inside the base of the exponents, the thing that gets multiplied. I'll go over it more later in the next video, so you don't need to worry about it too much right now. So anyways, now that we have this on the inside, we need to evaluate it, so we can find out what the imaginary part is. So we have this. We multiply both sides by 7. If we multiply both sides by 7, this becomes 7. We remove the fraction here. This becomes 7. Well, 7 minus 3 is equal to 4. And then negative 4i. And then we multiply both sides by the conjugate, which yields us this. And then we simplify. We divide both sides by 4 and then distribute this. That's what we get. Well, 1/2 the imaginary part of this. Well, first of all, the imaginary part of this is 7 over 8. Remember, we don't include the I when we talk about the imaginary part of something. And then 1/2 of that is equal to 7/16, which is B. So if you had any trouble, understanding any part of this explanation, I would encourage you to go onto the Art of Problem Solving website, find this problem, and look at some of the other solutions yourself. So this concludes the 5th video in my 6-part series for the AMC 10 tutorial. Thank you.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!